Hello. So, in the previous lectures we discussed about applications of arbitrary solutions of Stokes flows, and then some applications like the mechanics of swimming microorganisms. So, now justifying the title of this course, that is modeling transport phenomena of microparticles, we are going to discuss another application, that is modeling transport of viscous drops. Okay. So, typically when you hear about the word viscous drops, you can as a layman you can imagine several applications. In real life we come across viscous drops in variety of situations, right, like micro to macro level. So, drops and bubbles, these are sometimes time and often they are used one for the other and vice versa, but there is some basic differences which one can formally define. Okay. So, when it comes to applications like some gas bubbles in some soda. So, okay. So, that is like some gas is trapped inside a volume, okay, and external there is another fluid, right. So, basically these two are immiscible. So, in such case that is called a bubble. So, whereas if suppose there is a liquid trapped in a volume, so then it is a drop. So, that is a basic difference. So, you can imagine drops means you have a lot of examples in real life. So, today we are going to discuss about transport mechanism of such viscous drop. Of course, to start with we have a spherical scenario, okay, and then how the corresponding transport can be modeled. So, in order to model, typically we talk about spherical drop, let us say, in another fluid. So, then since these two fluids are immiscible, so we have to know what are the corresponding interface mechanism, right. So, we spend some time on discussing the corresponding interface mechanism. Okay. So, as I indicated, bubble means gas or vapor trapped in a volume inside another immiscible fluid. Then drop, so a liquid which is trapped in another fluid. Okay. So, there are several examples. Then you see several applications where suspensions of drops or bubbles, okay. And even in most of the propelling systems, rockets, etc. So, where liquid fuel is used, so you come across the impact of drops and suspension of drops very much, and these are also used in various mixing technologies. Okay. So, these are some other additional applications, for example, formation of uniform composites, that is where I said the mixing technology. So, to have a uniform composite, one has to have a fine mixing technology. So, and there should not be any deposit. So, they use some bubbles, etc., and then finally, when they burst, so you get a complete uniform texture. Okay. So, these are some spraying systems, chemical reactors. So, you can plenty one can give, and also these one can see some droplet phenomena when you have a motion of swimming microorganisms or blood flow. Okay. So, most interesting where lot of applications are oil industry. So, typically you can see oil in water or water in oil. Okay. So, this is the other scenario, and sometimes these droplets have see this is the water, okay, oil in water. So, this is oil. So, you can see, so there will be some deposits. So, these are the surfactant layers. Okay. So, that means when you have a droplet, you can just visualize, if you have a drop in a immiscible flow. So, then if you put some like contaminant concentration something, immediately you will see some particles will go and accumulate on the surface of that. Okay. So, they form surfactant monolayers, right. So, definitely they will impact the migration of the drop. Okay. So, that is applications. Now, Let us have a quick recall of the interface conditions in case of a fluid coming in contact with a rigid body. So, we discussed this is a kinematic condition where normal velocity is 0 if the assuming that the body is at rest. Okay. Similarly, this is the no slip condition. So, the tangential velocity is 0. Now, we need to discuss similar conditions when you have a fluid comes in contact with another immiscible fluid. Okay. So, in this scenario, since there is no mass transfer happening across, because both are immiscible. So, there is no mass transfer across the interface, therefore, the corresponding normal velocity exterior is 0 and interior is 0. Okay. So, this is not a good notation, we should have written two of them independently. So, suppose you have an interface where you have some exterior fluid, okay, with velocity u, interior let us say this is the velocity, and if this is the boundary. So, then since there is no mass transfer, because this is of viscosity mu I, this is of viscosity mu e. So, then what we are assuming is here u e dot n. Okay. So, of course, the corresponding directions of the n matters, but since we have homogeneous boundary condition, so that is immaterial. Okay. So, this is the kinematic boundary condition for each of the fluid velocities. Okay. So, now similar to the dynamic boundary condition, what would be the condition here, assuming the interface is stationary. Okay. So, dynamic boundary condition is intact. So, since you have a fluid motion taking inside, so it is expected that the corresponding tangential velocities are continuous. Okay. So, this is analogous to the no slip condition at a rigid boundary. So, you may be questioning this a bit initially without accepting as it is. So, how to justify in some sense, suppose, so you have fluid inside is also moving because it has an interior velocity, and then this fluid is also moving with an exterior velocity. Since the flow is viscous, this is very important for us. Since the flow is viscous, so the fluid layer which is close to the boundary, so will have the velocity of this boundary, okay, and the fluid layer which is adjacent, so they will have the velocity of this, and then these two have to be continuous, because we assume that the interface is very thin and there is no mass accumulation at this stage. So, hence we get T equals. So, this is the corresponding interface condition. Now, since this is a viscous environment, so are these the boundary conditions? So, no, naturally we have to discuss about the corresponding stress. Okay. So, let us consider such an interface with normal, and the corresponding interior we have given a negative. So, let us say the velocity is u I and the corresponding stress is indicated like this, okay, and the corresponding stress is this. Okay. So, when you have such interface, what happens to the surface mechanism? So, if you ask the question, it is natural to think even without much of physics, we say okay, surface tension plays a vital role, because the surface tension plays a role when you have a interface, not within the domain, right. So, naturally the stresses have to be balanced while considering the surface tension effects. Okay. So, that is the stress balance essentially tells. So, if some balances the stresses, so what you will see is the balance is something like this tentatively. So, you have an area, so where you are balancing the stresses, okay. That means the jump exterior to interior. So, this is the jump, you can say exterior to interior, plus also you have to balance the surface tension forces, okay, and this total will be 0. So, this is the fluid stresses due to the velocity and pressure, whereas this is the corresponding forces due to the surface tension. So, if this is on an area, this will be on a curve bounding the area. So, it is essentially something like this. If you have, and let us say this is in a 3D. Okay. So, then if you take a small surface element, okay, then there will be a bounding curve C. Okay. So, on this you get the corresponding surface tension forces. So, if one formally balances this, we get the corresponding stress balance. So, I am not giving you the formal proof, because it involves a lot of calculations, okay. But one can refer any standard book on viscous drops. So, some of them will be included in the references. So, one can get this derivation. So, what it tells is, for an arbitrary element, one can have the external stress minus the internal stress is balanced by essentially surface tension force is a surface activity. Hence, this gradient is having a special understanding. So, this is a surface gradient. Okay. So, if it is a 3D surface, let us say, and if you are on y equal to constant, this gradient is with respect to x y. If you are on x equal to constant, this gradient is with respect to y z, etcetera. Okay. And the curvature also affects, okay. Curvature will also influence, therefore, the surface tension and the corresponding interaction of the curvature. So, that is this. Okay. So, if you decompose this, normal stress is balanced by the surface tension times the curvature, and then tangential is balanced by the surface force, which is strictly surface gradient of the surface tension, because it is a scalar. Okay. So, if one assumes that there is no like surface tension is constant, it is not changing, then what you would have, so this will be 0. So, one would expect continuity of the tangential stresses, and in case of normal stress, you get a constant multiplied by the curvature, which depends on the specific boundary at hand. Okay. So, this is the additional tool that one has to consider when we have a fluid interface. So, now to proceed further, this is related to the mean curvature h of the interface by this. Okay. So, this is very standard notation. Then normal stress can be expressed in this form, and the tangential stress can be expressed in this form. Okay. So, now let us say it is a spherical. So, then correspondingly this will be simplified, okay, to 2 by A, okay, because both the R1 and R2 coincide. So, you get the corresponding. Okay. So, therefore, this is in summary, we have kinematic condition, normal exterior is 0, normal interior velocity is 0, tangential velocity is continuous. Then we have normal stress balance, and we have tangential jump condition, we call it, because there is, it is not continuous, there is a jump. Of course, here also normal stress there is a jump, which depends on the curvature. So, these are the boundary conditions which are used. We will see some scenarios where the surface tension is also varying, okay. But in this lecture we assume that the surface tension is constant. Okay. So, now let us consider one problem, which is just an extension of Stokes flow past a rigid sphere, that we extend it to Stokes flow past a drop, okay, spherical drop. So, we are considering Stokes flow past a spherical drop. So, you have a drop where you have fluid exterior with viscosity mu e and density rho e, and interior fluid you have viscosity mu I and density rho I, and we have a far field ambient velocity. So, once you have far field ambient velocity, in presence of the drop it gets disturbed, this flow gets disturbed. So, our aim is to compute the flow disturbance. Okay. So, in this approach there are two cases. One is you have an ambient flow, then flow past an drop. On the other hand, you can consider you attach a moving frame to the drop. So, then drop is moving with a velocity where you have ambient 0 velocity. Okay. So, both are equivalent, except there is a shifting of the frame takes place. Okay. So, in any case, so both the solutions are equivalent. Okay. So, as I remarked, this is nothing but modification of the rigid sphere problem. Okay. So, let us go for the assumptions. Drop is translating in another immiscible fluid with a given ambient velocity, there is no gravity, and we are considering r theta phi with origin as the center of the drop. Even though I have shown the frame like this, we are assuming it is at the center of the order. Flow is incompressible and axisymmetric, and inertia is neglected. So, essentially we are boiling down to Stokes equations. Okay. So, we assume for r less than a inside the drop we have Stokes equations, r greater than a we have the Stokes equations, and the superscripts denote flow exterior to the drop and interior to the drop. Now, since we have assumed axisymmetric, we introduce corresponding stream function, and we reduce the corresponding scalar equivalent equation outside and inside. So, since we have already discussed Stokes flow past a rigid sphere, so this is exactly following the same methodology, one can get this. So, basically we assume once we have eliminated pressure, we get the stream function. What is the stream function equation? So, we adopt that. Okay. And the corresponding separable solution in spherical polar coordinates is also very much available. So, for example, we must refer the book by Happel and Brenner, okay, which is listed in the references. Okay. So, we move on to the general solution to start with. So, you can see the general solution is expressed in terms of something called Gegenbar functions. So, these are essentially these are linear combinations of Legendre polynomials. Okay. So, for separable solution and the corresponding methodology, one should refer some books on PDE or Happel and Brenner. So, here G n and H n are Gegenbar functions of first and second kind, but one may observe that Gegenbar functions of second kind they are bounded, okay, with respect to theta. So, due to the boundedness with respect to theta, we neglect. Okay. We need a boundedness with respect to theta, and these are to be neglected. So, the leftover will be a bounded solution. Okay. So, correspondingly for interior we adopt some coefficients, and exterior we adopt some other coefficients, because this is the general structure. So, let us call it for interior with primes, and for exterior no primes. So, these are the general solution at this stage. Okay. Now, what are the boundary conditions? Since we are in a spherical case, u dot n is nothing but the radial component. So, radial component of the exterior flow is 0, radial component of the interior flow is 0. Then tangential component is continuous, which means here only the theta component, because due to x symmetry there is no phi component. Then the corresponding shear stress, that is tangential stress, is continuous. Okay. If you recall, we had jump, and the jump is nothing but the surface gradient of the surface tension. So, now here when we are writing this, we are assuming that surface tension is constant. It is not depending on any quantity. For example, surface tension can vary with temperature, okay, or surface tension can vary with concentration or a combination of both. So, in which case the surface gradient has to be there, but for the present problem we are considering surface tension is a constant. Therefore, the corresponding surface gradient is 0. Therefore, the corresponding tangential stress is continuous. Okay. And we have far field conditions. So, this is uniform flow along z direction. So, corresponding radial component and corresponding tangential component. You might be wondering, we did not use normal stress so far. So, we did not use any of them, we are simply stating. So, that is a remark, normal stress condition is not stated here. So, we will pay some attention to this, why we have not stated here. Okay. And this is a for interior flow the boundedness condition, we are not allowing any singularities. Okay. Now, we have introduced stream function, therefore, it makes sense to get the corresponding boundary conditions in terms of stream function. So, that is this is the normal velocity, tangential velocity continuity, and then tangential stress continuity on the boundary. Okay. Far field is given by this, the corresponding far field condition. So, corresponding to uniform flow, this will be the equivalent stream function. Okay. So, that is as I indicated, we are not commenting at this stage the normal stress balance and the boundedness. Okay. So, we go for the corresponding general solution, then use these boundary conditions. Okay. If you recall, for Stokes flow, what we have done, once we have a far field behavior, then all the functional dependency of theta is controlled by the far field behavior. So, correspondingly no point in considering the other functional forms. Okay. So, that means you have a complete basis, but we know that for solution only particular solution is contributing. So, the remaining we are throwing, because even if you consider and do the algebra, you get a homogeneous system which gives you a trivial solution. Okay. So, hence it makes sense to first impose the far field condition and then obtain restricted solution. Okay. So, that is what we do. Since far field is behaving like sin square theta, we assume each interior and exterior is of this form. This we have done very much for the rigid sphere case. Therefore, we have such structure. Okay. For interior and exterior. So, from primes we have to be consistent, J I means interior, E means exterior. Now, we use the far field condition, then we get D E is 0 and C is minus half. So, how did we do this? So, this we have shown earlier. So, we can discuss. So, exterior psi is given by A E by R, B E R, C E R square. So, D E R 4 sin square theta, but we have a far field behavior. So, this must go to half u or u infinity r square sin square theta. Okay. So, what we are doing? So, if we take r square sin square theta common, so this will be cube Okay. Now, far field has a functional dependency like this. So, far field should behave like this, that means we want this to be bounded. Okay. So, in order as r goes to bounded, as r goes to infinity. So, r goes to infinity. So, these two go to 0 they go to 0 as r goes to infinity. Okay. So, then C e, if C e is half u, if C e is half u infinity, then the flow goes to exactly what we are looking for, but this is the one which is making unbounded. So, therefore, this implies d is 0. Okay. So, this gives you d is 0 and c is minus half. U can be 1 here. If you non dimensionalize, simply we get c is half. Okay. So, then interior solution we need a regularity. Okay. So, correspondingly for interior solution we consider a I is 0, b I is 0. Therefore, the reduced stream functions exterior and interior are this. So, we do not have u infinity because we are working in a normalized situation, non dimensionalized. Okay. Now, rest of the boundary condition, what is the boundary condition? Tangential stress balance. So, we have, once we have this, we use the tangential stress balance. Okay. So, we have to compute dou psi dou r, then 1 over r square, then dou by dou r, and mind you. So, there is a coefficient viscosity mu e and then this is mu I. So, therefore, the terms not immediately cancel, because you have, they will not come up as a common, because there is a ratio of mu e and mu I involved. So, this algebra can be done on this, because you have only 1, 2, 3, 4 coefficients, it is very straightforward. Okay. So, we can determine these 4 coefficients. You can see as I indicated, mu is involved in these coefficients, which is the ratio of the viscosity. So, that is interior to the exterior. So, again I am mentioning this algebra is very straightforward. Computing the tangential stress balance is very straightforward, nothing much, just 2 partial derivatives on psi. Okay. So, you can do it very easily. To realize that, we get these coefficients. So, once we have these coefficients, we have the corresponding stream function exterior and interior. Now, this is the case of drop having viscosity mu I and mu E. Okay. And we have mu, which is the ratio of mu, okay, mu E. So, if you want to get the limiting case of, this is a drop, if we want limiting case of rigid sphere, then we go for interior should be highly viscous, that means mu I goes to infinity. In other words, mu goes to infinity. If we take this limit, we can retrieve the corresponding solution for the Stokes flow past a rigid impermeable sphere. Okay. So, now you should ask the question, still we did not use the normal stress balance, okay, and we manage the solution, right. So, what is the scenario here? Our assumption is, who is keeping the drop spherical, right, surface tension is keeping the drop spherical, right. So, under this assumption, the normal stress balance is automatically satisfied. Okay. So, if you deform the surface, so then the normal stress balance becomes an additional condition, and using that one can determine the corresponding deformation. Okay. So, this involves some algebra, but I will just try to explain a bit. So, before that, you can see this is for a particular viscosity ratio, streamlines are given. So, you can draw for various viscosity ratios and see how the streamlines behave to get some physical insights. Okay. So, as I indicated, normal stress balance over determines the system if one assumes a sphericity of the drop, whereas, if we assume that the drop is deforming, then normal stress balance can be used. Okay. So, when I say that, so this is spherical. Now, suppose something like that. So, this is some function of theta. So, example say. Then we have normal velocity condition, tangential velocity condition and tangential stress condition. So, on the spherical part we have got the solution, we have determined the coefficients, but suppose if you assume the drop is deformed like this, where epsilon is the corresponding deformation parameter. Okay. Then one can use normal stress balance and expand these. Okay. How do we expand in terms of this R? We assume that epsilon is that is small perturbation. Okay. Small perturbation, it is slightly deformed. So, which means we consider terms up to order epsilon square. Okay. So, then how do we expand various polynomial solutions? Suppose you have 1 over r square, this is nothing but 1 over a square into 1 plus epsilon cos theta square. So, this is nothing but 1 over a square 1 minus 2 epsilon cos theta plus order of epsilon square, with the assumption that epsilon is much smaller. Similarly, suppose we have such, this will be 1 over a 4 1 minus 4 epsilon cos theta. So, this is a case of small deformation. So, to balance the normal stress, we need the pressure. So, in terms of stream function, from the momentum equations we can get this compact form. Okay. So, you can see this is the r momentum and this is the theta momentum, and we have anyway we have the corresponding stream function. So, from that one can integrate to get the corresponding pressures. Okay. So, this one has to do the corresponding calculation. Now, once you integrate the pressure, pressure is unique up to a constant. So, these are the corresponding constants. Okay. And this is viscosity ratio, and this is expressed in a dimensional form, that is why you are seeing u. Okay. Now, once we have, we compute the normal stress exterior and interior. So, what is the normal stress expression? U r. Okay. So, we have integrated the pressure and then we have velocity. So, one can compute the corresponding normal stress, then balance the normal stress. You can see why we are getting 2 sigma by r, because we are talking about a sphere. So, therefore, the normal stress balance reduces to 2 sigma by r, and where r equals to a, we have this. Okay. So, as I indicated, this we are expanding on this deformed sphere, okay, deformed surface. We have taken a equals to 1. Essentially, you this minus this mu times this equals to 2 sigma by r, where r is this. So, now as I explained, we go for such a small deformation, then correspondingly equate terms having similar functional dependency. So, the constant term is equals to 2 sigma, while sigma is constant here, then the corresponding coefficient of cos theta will lead to this relation, which means we have determined the corresponding shape parameter. Okay. So, what we intend to do here is, for a small deformation like this, one can determine the shape by balancing the normal stress. Okay. So, this is not very straightforward. I am sure you may not appreciate so much, because it is a lot of algebra involved. So, that would take some time, but it is doable. It is very routine calculation. So, we will try to give some relations in the appendix, so that you are comfortable in following, and then you can continue this algebra. Okay. So, if you do it, then you will be ready to handle some research problems. So, that is a basic intention that I did not give you the routine calculations here. If you do it and then arrive at these expressions, you will appreciate and you will be ready to solve some research problems. Okay. So, this is the case of spherical drop migrating. So, when we said here migrating, we can compute the corresponding migration velocity. So, how do we compute? So, we have to compute the drag forces acting on the drop. The process is similar to what we have done for Stokes flow past a rigid sphere. So, once we compute the drag force, we balance the net forces to be 0, then we get the corresponding migration velocity. So, I hope you get some idea about migration of viscous drop, of course, spherical in an ambient flow. And in the next lecture, we try to consider the case where you have surface tension depending on some activity like temperature or concentration. Until then, thank you.